Good morning, everyone. I'm so happy to see all of you here today, and you know why, right? Because this is the very last session, apparently, for you. And if you are still here, you definitely was waiting for it. And for sure, I'll try to meet your expectations. My name is Eugene. I'm a WAN escalation engineer based here in Brussels, Belgium. I deal with escalations from TAC engineers, and I'm from Catalyst Engineering Business Unit, which is basically routing, SD-WAN and routing. First of all, I want you all to join to a WebEx Teams space, because there you can ask your questions. I have so much of a material, a lot of material, and if you start asking questions now during the course of a session, I won't be able to finish it on time. That's why please post your questions. There are my colleagues who may be answering them. If still some questions are unanswered, I promise you to follow up on them all in the WebEx Teams space, okay? Or we can certainly talk after the session. Let's start. And first of all, let's establish baseline and objectives. This is, as I said already, very deep technical session. So that's why I expect you to all have at least basic level of SD-WAN understanding. I'm not going to cover basics, maybe only just some of them, minimal concepts, if they are really needed to cover troubleshooting, right? The session main objectives, first of all, to demonstrate useful troubleshooting techniques and tools, especially new tools if you are not familiar with them. The second part of the session will be also to share the experience and interesting or some strange cases which we've seen in the field, so you can avoid similar problems in your production networks. It's not a comprehensive guide, right? It's rather kind of limited. Even in such a long session of 90 minutes, I can't cover all of the scenarios, certainly. And consider, hence, this session rather as like small cookbook for troubleshooting, but not a tour de force. What do I mean by this? Tour de force, it means that you may see that cool, you solved that issue, you showed it on few slides, but in fact, in reality, I'm just trying to explain it in a very condensed manner, but for us, for TAC or for escalation team, some of those cases, by the way, it's all based on real life scenarios. Sometimes it took days or even weeks to resolve. So don't get upset if you can't follow, it can be. The second main objective for this session is also to provide you with slide deck, which can you review later, right? So keep it, make sure to download it, keep it because it may be useful during your day-to-day troubleshooting exercises. So, the session main objective is about centralized control policies. But whenever it's possible, I'll try to cover also localized policies, for sure, because the topics are very closely related with each other. And main topics covered is the troubleshooting workflow, as I said already, troubleshooting toolset, common pitfalls, and challenges we've seen. And this is heavily CLI-based, right? We like CLIs, we like old school, but certainly UI tools will be covered. As a recommended prerequisite for this session, since control policies cannot be really discussed separately without routing, there is my older session available in Cisco's on-demand library on routing troubleshooting. But we will certainly cover some part of it here. You may want to check the on-demand library later for this session. And agenda, you can see there are hyperlinks. You will have a slide deck, so we can go through the hyperlinks to the respective sections of the slide deck. And without further delay, let's start with troubleshooting basics for policies. But before that, I want to emphasize one important change, which happened already quite a while ago, right? We renamed it, we manage a network management system to Catalyst SD-WAN Manager. We renamed it WAN Orchestrator to Catalyst SD-WAN Validator, vSmart to Catalyst SD-WAN Controller. So it's too long to pronounce, right? So I will stick to legacy names, if you don't mind. Why? Because I like them. Okay, but seriously, it's not because I just like them, but because in all of the CLI outputs and internally within the source code, we will still use old names. And we are not going to change this, just obviously for required compatibility. We don't want to break your automation tools and so on. So internally, it's still called vManage, vBond, vSmart. And I will hence use those names interchangeably. Quick policies recap before we start discussing troubleshooting. So what type of policies we have within SD-WAN overlay fabric? First part is centralized control policies, which are in fact, just centralized policies, which are in fact divided in two subgroups, topology and VPN membership policy. Yeah, by the way, who remember what is VPN membership policy? Okay, just for those of you who don't remember, this is basically a subset of control policy, which is all these applied on the outbound direction in controls which VPN labels are advertised to particular WAN-H devices. Another question, who knows what UX 2.0? Perfect. So UX 2.0 basically is an official name for policies groups and configuration groups. In an attempt to simplify user experience, in UI, we call that part just topology. So they are all separated. VPN membership policies and centralized control policies is just in the settings topology. And traffic rules. Again, there are classic traffic rules like application-aware routing policy, data policy, and CFLOD templates. But in the UX 2.0, we call them just application, prioritization, and SLA. Alpha under the hood still details and complexity remains, right? So we still split those policies into data and application-aware routing policies. How are they configured? Usually, you will define them on vManage in UI. Then, with help of netconf over SSH, over control connections, those rules or policies will be sent to vManage controller, right? And vManage controller, depending on the policy type, it will either enforce it locally, or it will send it for processing as a part of OMP update packet on VH. On VH, we have a special type of route information base, which is called volatile RIP, and it will store in memory data and application-aware routing policies. In contrast, we have also localized policies, which are simply parts of device template. And as an example of them, you can call access lists, you can call zone-based firewall policies, and so on. In UX 2.0, again, in an attempt to simplify this, we call this, we put everything under the policy group, and there you will find next generation firewall rules, which are a combination of zone-based firewall, plus unified IPS policies. SIG templates are there also, and DNS security. The difference with centralized control policies is that, as I already said, we are part of a template, and hence simply push it from where we manage directly via netconf session to WAN-H device. The next important concept, before we start discussing policies troubleshooting, is very well-known concept of building blocks for policies. And the first part is the groups of interest which you perform your match based on, right? It can be prefixes, TLOCs, colors, SLAs, and so on, depending on policy type. You combine them together, you define the policy, a set of sequences, right? A set of sequences which define actions applied to particular match conditions, to particular group of interests. And finally, you define the direction of policy application. If it is centralized control policy, from a perspective of vSmart controller, inbound to vSmart controller or outbound to vSmart controller. If it is data policy, then from a perspective of service side on WAN-H device, from service side or from tunnel, or both. And together we are enforced across the overlay certainly. Now, knowing all of this, we can define generalized policy troubleshooting workflow. And again, I'm not going to read through all of the blocks of that workflow. This is mainly for your reference. But what I want to draw your attention to is that it consists mainly of two major parts. The top part is relatively simple, because this is everything we do in vManage while configuring the policies. And some checks here, vManage will do for you automatically. If you see such an icon, right, it means vManage will perform automatic check and warn you in case you are going to do something bad. Not really bad if you are doing something which is in contradiction with a workflow. And the second part, once policy defined, we need to install it on the corresponding device. Let it be or let it be the smart controller, or let it be one edge device. There are a set of actions which I propose to follow as a troubleshooting workflow. We will discuss all steps defined in that workflow in a coming section in details. So, top part. From perspective of vManage, what we usually check? You cannot apply your policies if you don't have the smart template assigned. So very first thing, like top-down troubleshooting approach, right? You verify the basic things first. You verify that you have a template assigned. And then you verify that you have a defined policy which is activated. Obviously, if policy is not activated, it's not enforced. If we are talking about UX 2.0, the approach is a bit different. Under the configuration topology for centralized control policies, for topology policies, to be more precise, you verify also that policy is activated. But if you did any changes to the policy, with UX 2.0, it's a two-step process. Once you change the policy, you need to ensure that you deployed it, that you deployed your changes. So it might happen that you apply it configuration and then it does not work. But in fact, maybe you simply forgot to deploy the policy. If you attempted to activate the policy while device template is not attached to the smart controller, this is what vManage will do for you. It will warn you right away that, look, you cannot activate the policy because there is no template. Simple as it. The other interesting and helpful thing is that device itself, in this case it was my smart controller, will do some verifications for you before attempting to activate the policy. So it won't break the traffic flow with some inconsistent changes. Like here, we were trying to activate the policy while we had two site lists defined. Site list for site number 11, and also some kind of site list called branches. It happened that site list 11 contained the same site ID as the bigger site list branches. This is not allowed, hence the smart controller responded to us, and this is more or less human readable error, which you can understand here. As for localized policies, this is certainly simpler. Localized policies are part of a device template, so you need to ensure that you assign it corresponding policies. This is, let's say, access list policy. This is zone-based firewall policy, for example. Compared to UX 2.0, there is a catch, exactly same catch like in policy groups. Yes, exactly like in topology. For policy groups, they are all combined together, and you need to verify that it is assigned, but then you also need to ensure you deployed it. If it is configured already, when you change something but have not deployed, changes won't take effect. There is yet another catch also, which is not very obvious. I told you, right, that this part, zone-based firewall, next-gen firewall, secure internet gateway, DNS security, umbrella security, this is in a classic UI basically part of device template. And hence, if there is no device template attached, if there is, in terms of UX 2.0, if there is no configuration group attached, and you attempt to deploy policy group, you won't be able to do so, obviously, if there is no template attached, right? Just like the same with vSmart. vSmart must have device template attached, otherwise you cannot activate centralized control policy on vSmart. And if you attempt to do something which is not supported, again, in this case, it's already vManage. It won't even try to push the template. It will check the model, Young model, and according to the Young model, apparently it's not possible to configure something. Some issues with IS path list, apparently. And if you're interested, it was just a typo in the configured IS path list. That's why vManage could not validate that Young model. OK. And last but not least thing in the top block of troubleshooting for vManage part, and I also call this as one of the most important troubleshooting capabilities, is to verify the preview section of a policy. The preview will give you CLI representation of your configured policies. Why is it important? Because I'm really convinced that it's a critical skill to be able to read it in a CLI format. Sometimes something which you define it in UI may not be really understandable. But if you can read that part, you already, with 80% likelihood can solve logical mistakes in your policy at least. That's why always before applying the change, just scan through your policy preview in CLI view. We will also use that text in verification on device side. So you may also sometimes need to save it into a text file, because then we will compare it with outputs from device side. As for the device side, so you remember the top part, we finished it with top part of troubleshooting workflow. Now we want to talk about the bottom part. And certainly before we do so, again, I must remind you a few concepts about, in this case, centralized control policies. And most important concept will be the direction of policy application. Why? Because, for example, here, in this example, I have a policy action applied on inbound direction, right? For example, I want to filter out completely any advertisement from that router, right? What does it mean? It means that once it is filtered, there will be best path selection performed. And that prefix obviously won't participate in best path selection algorithm, right? Finally, we will advertise that prefix to the rest of the devices. And compare it to an outbound direction, we will get a routing update, we will perform best path selection. Here, best path selection can be the thing which will eliminate some paths. Because if that path, for example, from the device on the bottom is not the best path, it won't be subject. My clicker died, OK. My clicker died completely. So we will apply policy action on the remaining prefixes only after the path selection. And then we will advertise the rest to the devices which have no outbound control policy applied. Oh, it works now again. Maybe the distance from the station was too far. If you see such an icon, it means this is given for your reference. We are not going to go into that slide in details, because on the upcoming slides, I'll give you examples of all of those commands and why they are important. Let's just have a bird's eye view. So what we check on the smart controller, we verify if configuration changes committed to a database, to a configuration database. We will verify OMP peering, because if there is no OMP peering with some OneEdge device advertising the prefix, or there is no OMP peering with receiving device, obviously we cannot apply the policy to that advertisement. Then we will verify which policies assigned to a particular device. And if you remember, I told you we always have to check CLI preview on vManage. We will compare that preview with what we actually see on the smart controller. Are there any inconsistencies? This is what we are verifying here. Finally, we can verify logic. And if still, up to this point, there are some issues, if you cannot identify the problem, likely this is an issue with routing. And then I direct you to my other session on routing troubleshooting. Certainly, you may not remember that session. That's why in a very quick condensed format, in just one slide format, this is a recap of generalized routing troubleshooting algorithm. One of the examples is, what if we have a route missing, let's say, on the destination SD-WAN router, and the advertising router on the service side, this is like normal RS router in autonomous mode, advertising some prefix. How and what we are going to check there? On the very first step, certainly, you verify here if we have a prefix in the routing and forwarding table, and the same here. When we verify if it is absent, we verify if maybe it's in the OMP table. If not, maybe we have some issues with policies on this smart. Also, we verify TLOC information, because you remember, TLOC table decoupled from vRoute table, routing table. If there is no corresponding TLOC for the route which is pointing to the TLOC, we cannot install it into the routing table. So that's why we verify TLOC here. There may be a problem with TLOC itself. TLOC may not be resolved if there is no data plane session with remote destination. If there is no data plane session between those two routers, right, TLOC will be unresolved. And we hence need to verify BFD sessions between them. If there is issues with DVD sessions, there is yet another part of a troubleshooting. Major part is data plane troubleshooting itself. Raise a hand if you attended to my session on Monday on my tutorial. So those of you who attended to the tutorial, we covered that data plane troubleshooting as well. And then, if it is localized policy, maybe there is some kind of device on that side, which is, again, autonomous mode on the service side, and we want to advertise OMP to some other service side protocol. We will verify, maybe we have a filtering here, right? On vSmart, it's simple. On vSmart, there is only 2 tables, and on vSmart, we don't care about reachability information. We just pass the prefixes between 1H routers, and hence we verify only OMP table and TLOC table. OMP vRoute table and TLOC table. Last resort. Up to this point, maybe he was, again, unable to identify the source of problem. Maybe it's somewhere deeper. And that's why there are debugs available, various debugs, which sometimes may help you, for example, to understand what kind of policy was applied or not applied. We are not going into details of what exactly may happen here, but let's just briefly cover how to enable those debugs, because the behavior changed in 20.12 version. If you get used to previous versions, when you enable debugs, we are stored under the temporary folder, which is actually the partition mounted in memory. So it means after the reload, all the logs are lost. We decided it's not good, obviously, and changed the behavior. So in 20.12, logs are stored on the permanent storage. But certainly we cannot continuously write to the permanent storage. We decided that it should be configurable, right? And to enable it, there is a knob to enable disk logging in the newer versions. To view them, there are different approaches. If you are comfortable with Linux CLI, you can use tail -f, or simply show log from SD1 shell. Or you can print logs on the terminal as soon as they appear. Debugs. OK. I promised you that we are going to take a look into the details of all of those commands, and more importantly, what exactly you need to look at in those outputs. The first thing first, right? So we configured, I remind you, on vManage, we configured all policies. We generated CLI preview. We checked the CLI preview. Now, you need to check the configuration database on vSmart if you are configuring centralized control policies, and ensure that the changes arrived from vManage and recorded into the configuration database. So that's how you can verify it. Number 0 will be the very last change arrived to the smart controller. And client will be netconf. So it means it's not something was configured from the CLI manually. And obviously, you compare everything here with what you had on vManage CLI preview output. Step number 2, we are checking if there is a peering with the source of advertisement or with destination of advertisement. How to do it? Show OMP peering, and obviously we verify that the state is up, and number of received routes, maybe we are not getting anything from the peer. Then the next step, there is very interesting and useful show support level command. The big disadvantage of this command is that it is giving you a lot of very long output at once. That's why you always must apply some filtering. And what I propose is to filter based on keyword POL. It will give you a few lines of that output, which will contain information about policies applied to a specific peer. Again, since it is support level command, which was introduced long ago and then later made available for troubleshooting to everyone, there are still some legacy names for policies, but you still can understand them easily. Site policy is what? It's a site list, right? Route policy is basically a control policy. Data policy, at least here we have a match. Data policy out. PFR policy, what do you think is PFR policy? It's application-aware routing policy, right? PFR is very similar to what application-aware routing policy is doing. And this is a VPN membership, and this is CFlowD template. On step number 4, we also verify how information look like in showrun output. We already checked configuration database, but it won't hurt if we double check also how it looks like from showrun output. And here, the example how to check particular policy, and then the direction of its application And here, elements of that policy, like site list, how you can check it from the CLI. Step number 5, logical verification of policy. For example, here I want to verify my control policy what will be applied for the advertisement from site 40 to the default, if site 40 advertises default prefix list, right? And I see that there will be an action to set preference, and we set some kind of service. Some kind of service, yes, certainly the number does not say anything to us, but this is service chaining. Some kind of service chaining applied here. And the sequence will be 31. So then later you can go to your policy and verify, is it something which I'm really matching on, or maybe I did a logical mistake and I was supposed to match different sequence number. That's how you use this policy. More details, you remember, right? The next thing, if we still haven't found anything up to this point, we start to troubleshoot on routing, but I'll also cover this partially in part number 2, when we will be talking about interesting scenarios. That part is clear, right? Centralized control policies. Now we have data policies and application-aware routing, which are slightly different. Slightly different because despite that we are also sent to vSmart, but when vSmart converts it into XML representation, pack it into OMP update packet, and sends it to 1H router. Then policy is enforced on 1H router. There are also, like, just in few words, some most important concepts for troubleshooting. This picture should be very well known to you already, I hope. Who saw it already? Perfect, perfect. But anyway, there are some people, for those of you it will be new, so what is most important for us is that on step number 2, we have centralized application-aware routing policy. And later, on step number 3, in order of operations, we have data policy, which technically can override decision taken by application-aware routing policy, right? It's not that simple. Starting from version 20.6, we decided that we should simplify it. Yes, simplify. Actually, it is making behavior of policies when we have both application-aware routing policies and data policies configured together more predictable. I'm not going to read through the whole of the workflow. This is again for you during your day-to-day troubleshooting. But the most important concept which you may need to remember, data policy makes final decision with consideration for application-aware routing policy. This is a behavior starting from 20.6, which was published long ago already, kind of long ago. So data policy won't completely override. It may, but it won't completely override. It will try to take into consideration SLA match conditions from application-aware routing policy. Let's go into a bit more details, even deeper. And what if we have to need to understand, if we want to understand logic of application-aware routing policy tunnel selection? This is a workflow I prepared for you as well. Again, I'm not going to read through all of it. The only interesting part I want to remind is a new feature which appeared in 2015. There is also slight detail, slight devil in details. Let's call it remote preferred color, right? In addition to so-called preferred color, which is basically locally preferred color, we introduced the concept of preference about remote color on remote 1H device. It can coexist with locally preferred color, that's for sure. We simply define local or remote, local and remote if you want. But there is a catch. If you have configured fallback to OS path, which is also called best of worst, the feature which allows you to fall back to not so bad path out of REST, which does not comply to our SLA requirement, right? And you configured remote restrict. Remote restrict keyword won't be applicable here, right? Because the idea is that we still want to forward traffic somehow. Maybe not via the best path to a remote destination, but still we want to forward it. That's why even if you configure it restrict, you can configure it. CLI or vManage UI won't restrict you from configuring it, but it won't work. It's not a software issue, it's expected behavior. So remote restrict applicable only in non-best of worst conditions, non-best of worst configurations. This is the thing I wanted to draw your attention about that workflow. Okay, from vSmart perspective, I told you, right? centralized control policies and data or application-aware routing policies are very similar. We troubleshoot the same. We check commit changes to the database. We check peering, to which we are going to peering with 1H device to which we are going to send the policy. We check if policy applied. We double check if policy CLI representation is very matching to what we've seen on vManage. Right? So it's everything like we've seen before already. No difference with troubleshooting approach. But that's the thing. Since we need to transport those policies as a part of OMP update packet, and they will be converted into XML representation, into XML data format, we need to verify so-called XML policy crafting. And you can also do it with help of show support command. We will see examples. So what about 1H part? vSmart send OMP update packet. Now it's turn for 1H device to process those policies. What are we going to check here? Similar thing, if we are localized policies, then we will verify if it is a part of device template. If it is from OMP update packet, OMP policy packet, we verify show SD1 policy from vSmart command. Next, we want to verify if logic of policy is correct here from the point of view of 1H. There is useful command for this as well. And there are also approaches on how to verify that actual data traffic is matching to a policy. Few of them. Approach number one, you can use a counter. Most likely well known for you thing. You may accept or decline, or accept or drop action. You can configure a counter, which will simply count packets. We will see examples of it. Approach number, variation of this approach. Yeah, this is how to check the counter. The second variation, you can use log action. We'll also see examples and difference in between counter and log action. And the third thing is like, I call it heavy artillery, right? Something which you will use in case if those two are not enough. We use detailed troubleshooting tools like packet trace. It's not a packet trace, by the way, which you may know from very old days of CCNA, right? When you was preparing maybe for CCNA and was using packet trace to simulate networks. It's a packet trace tool on CLI, which we are using to trace packets passing through the hardware on the device and to understand which features are introduced or which features are applicable for the traffic. Or NWPI from vManage UI, which is also very powerful, and I'll give you examples when vManage NWPI is better than packet trace. Other useful tools, this one you're certainly aware if you dealt with application-aware routing policies already, just to how to verify SLA statistics. Those things you may not be so aware as compared to this one. We can enable flow visibility, which is basically not flow, to verify the egress interface is taken for the traffic. It's basically useful, but in particular, it's useful when we want to verify flow symmetry. If flow is egress through, let's say, gigabit Ethernet, one interface, if it returns through the same interface, this can help us. And there is yet another variation of this command, which is called up forwarding, but you need to enable policy application visibility for it, which will tell you also a classification of the application. I promise you to show examples. So, up to this point, again, just like with vSmart, what if we were unable to identify any issues? Right? We will proceed to policy programming low-level verification. Since this is advanced level session, since I'm from business unit, basically I'm a software engineer. I want to show you some interesting examples of how we troubleshoot deeper on the platform. And just a picture to draw your attention, right? My cat is trying to investigate the apparently old VH router. So centralized data and application-aware routing policies troubleshooting examples. That is the step number 5 from the smart perspective. I don't repeat all the first 4 steps because we are the same for control policies and for data application-aware routing. On step number 5, we verify policy crafting. How was it translated into XML format? And what I propose to use is the same command, show support OMP peer, But then, since there is no command called section like on iOS XE, right? But at least you can use multiple filters at the same time. I propose to filter starting from policy received until the keyword statistics. You will see more or less human-readable XML version of your policy, right? So verify that at least, for example, there are enough sequences compared to what you've seen. Verify if there are exact same number of sequences compared to what you configured from vManage as vManage UI. At this point, announcement OMP update packet arrived on 1H from vSmart. What do we verify here? For example, here I have very simple policy, and I want to verify if it was arrived and install it on 1H device. This is what we usually do. Show SD1 policy from vSmart, right? Step number 2, how to verify which egress interface or next scope will be taken for particular traffic. So, for example, I want to know what will be the direction taken for apparently DNS traffic to Cloudflare, right? UDP, port 53. So it also will take into consideration application match conditions. That's why this command is so useful. It's not just showing you, like show IP route, which direction for the destination will be taken, but also will take into consideration application, ports, and so on, which we may use as a match condition for data policy, for example, and tell you what will be the next scope IP address and its interface. And certainly you want to know what is the example of a bad state, let's say. This is the thing which you should be worried about. If you see that we can determine remote IP address or egress interface name, and you see a black hole, we are in troubles. Then we may need to continue troubleshooting on deeper level. Maybe we need to check policy programming on device level. About counters, right? Counters are useful troubleshooting tool. So here, for example, I made a policy which is matching everything, sourced from any IP addresses, and I want to count those packets. I did a ping to a destination from a service side, from VPN1, and then I checked number of packets matching. There also will be a default counter, which will count all of the packets which are not matching to the default sequence. Since I have default accept action, it will pass them without counting in that counter. It means you can be flexible, you can define source IP, destination IP, and so on, and also count packets more precisely. Now let's compare it with logging, with log action. Exactly the same policy. I want to know what will be the result of that action. And I did an SSH to some destination host. The important limitation about logging is that we are not going to log everything. It's not like debug IP packet on the old iOS, right? We are not going to log everything. We will log on the very first SYN packet. So despite it, obviously, SSH used multiple packets because I was able to log in, I was able to exit from the shell. So it's more than one packet, obviously. We logged only one packet. There are no more log entries. But usually it's already enough to get a bird's-eye view idea on what is going on, which policy, sequence, destination, source, and so on. Step number 3, right? Policy troubleshooting tools like packet trace. Time to talk about more powerful machinery. So this is the packet trace. To use the packet trace, usually you will define match conditions. You don't want to trace everything, right? You want to know what will be the action taken for a specific source and destination. This is how you define the match conditions. You can even use that tool to perform packet capture and then print it on the hex format to the CLI of your router. Or alternatively, you may want to trace only packets which are dropped on your router. Then you may need to know the drop ID. And there is a command which will tell you what are the drop counters seen by the data plane. On the left column, there is an ID which you can specify as drop condition for the packet trace. You can check statistics, and certainly in the overall statistics, it will tell you how many packets we're matching. Then you typically stop the tracing with condition stop command, and you can clear all conditions, so you can define them again for a new attempt. In the summary output, it will tell you Those are packets which are matching and in summary states if we are forwarded or not, and usually a reason if we are not forwarded. Here, specifically, I want to draw your attention to a drop code of 525, which is called no stats update. What's this? It means we are not updating any counter in QFP data plane. Because this is BFD return echo packet. Yes, we are dropping it, but it is supposed to be dropped. It's not something which we want to count, right? We send echo request, we receive echo reply, we are dropping that packet, and this is expected. And details of a specific packet, let's say if you want to know details of packet number 4, we can do it as well. But let's take a look at the more practical example, right? More practical example. I have an output of show platform packet trace summary, and when I check it the packet number 0, what can we see here? And surprisingly enough, we can see everything what is happening with this packet. Apparently, I have an access list on the service side, which is classifying packets based on some conditions and setting the forwarding class for quality of service, and setting the precedence-free quality of service class. Then I can see my DPI application, my DPI engine. In this case, it's nbar. And if we classify traffic, if we classify it from the first packet, then we can see all policies, more importantly, applied in sequences which we hit by this traffic. Selected remote destination color, local destination color according to the policy. And then on the egress direction, since we set a precedence class, we will put it into a corresponding outbound egress quality of service queue, right? Apparently, we are using IPsec encapsulation here, and this is finally the last step. We will put interface on the wire of Gigabit Ethernet 3. Yet another practical example. Imagine you have a router with multiple connections to your data center, over the MPLS tunnel and over BIS Internet tunnel. Interface in green is our service side interface. And you did a packet trace for a specific source and destination, and you see something strange happening here. Traffic was following Gigabit Ethernet 2 to Gigabit Ethernet 1, which is MPLS, and then, for some reason, we switch it to Gigabit Ethernet 3. We want to know why it's happening. Why traffic is not following the same destination? Because router typically doing the flow-based load balancing, right? We are not doing per packet load balancing by default. We expected to see that flow to follow through Gigabit Ethernet 2 to Gigabit Ethernet 1 by default. Why it happened? And let's check. We check it. We will compare packets. We will compare very first packet. We will compare very first packet hence, and then the packet which went into different destination, which was following different interface. And what do we see here? The difference between them will be that on this step of DPI, we can see that classification state was not final, and hence we cannot determine particular sequence number for our application-aware routing policy, and we considered all available tunnels for traffic which we don't yet know. And then we'll compare it with packet number 4, which went into Gigabit Ethernet 3. The difference will be that at packet number 5, apparently it was a new flow which was not seen before. We managed to recognize it, but it was an SSH session, right? And then for SSH, there is a sequence configured in the application-aware routing policy, which told us that we have to follow BIS Internet path. And then we started to follow BIS Internet path. This is an interesting example because maybe you're aware about the concept of flow thickness. It's not applicable in this scenario. When traffic follows the overlay tunnels, we don't apply the concept of flow thickness. It will only be applicable in case if we have DIA or secure internet gateway circuits. And if you attended to a session of my colleague from TAC, Luis, earlier today at 9 o'clock, you may know already a bit more about how the classification works here. I'm not covering this part, right? Okay, network-wide path insight. Packet trace, as you probably notice, it is quite an interesting and quite a detailed tool. But we have something even better. It's introduced, I think, in 20.9 already, and this is the tool which I call packet trace on steroids. Why packet trace on steroids? Because it's so powerful that it can do the packet trace all at once through your overlay. If packet trace typically you will be doing on per router basis, let's start from bespoke one. If traffic goes to the hub, I will trace on the hub. If it is on the hub, let's trace on bespoke 2, and so on. It's tiresome. And sometimes you may miss some important details while trying to capture on one, then on another, then on the third one. Here, packet trace will do it all at once for you, with help of so-called metadata header, which will mark the packet we want to trace and enable kind of packet trace functionality across the whole overlay. To do so, we use vManage as an orchestrator. So you define similar kind of match conditions. You define site ID, which you will start your trace with. In this case, usually it's a branch. VPN, you may define source and destination prefixes and click Start. Once we have enough information, once we captured some flows, you can click on the View Insights once packet trace started. You can click that button, and you will go to another section, which may show you something like this. Typically, it will contain upstream flow, egress flow, and if there is a return packet, it will also contain a downstream flow. And you can go even in a bit more details. If you click on that part, on the advanced view, you will see something very similar to packet trace, with the only difference. And WPI won't trace all packets. It's not really necessary usually. That will trace only the first packet, very first packet, and the last packet, which we had a final DPI classification, right? So if classification is final, for the whole flow, we will trace only one packet. It's enough already because we have a final classification here. We'll have examples of NWPI in the second part. Remember, we are still within our troubleshooting workflow, right? We are still within that workflow. And step number 4, there are some useful troubleshooting tools. What are we looking in? What should we pay attention to when looking to those tools? Here, as I told you, it's most likely quite well known to you already. You just check packet loss, latency, jitter for a particular destination and particular color. A more interesting thing is about cFlow data. cFlow data, as I told you, will tell you egress interface name and egress interface name. So where traffic arrived and each interface it followed when it was sent to. But since I don't have application visibility enabled, I cannot determine precisely which application family it was. If I enabled also flow visibility, application visibility, you will see slightly different output, which will also tell you the application, obviously if it was classified already. Low-level verification. Finally, we go deeper. And this is, by the way, not a stock photo. It's a photo of a rabbit hole near the Brussels office. Are you ready to follow down the rabbit hole with me? Quite a few of you. OK, but let's do it anyway. You know what? But before we do that, let's briefly discuss software architecture, because without understanding of software architecture, it's already confusing, but it may be even more confusing if I don't remind you of the software architecture. Usually, any kind of router, not essentially Cisco router, consists of 2 parts: control plane and data plane. Since Cisco Catalyst SD-WAN is hybrid SD-WAN, we still have part of a control plane running here, right? The logic, the controller separated, but still we have routing tables, we have routing protocols running here, hence we have some control plane. And we have a data plane, which we call QFP here. This is how it looks in a bit more detail. So control plane is a set of various daemon services, which are executing various functions. And this is the data plane, which we call quantum flow processor. The key difference between Cisco platforms will be that we either have a dedicated CPU to do the forwarding, or we even have a line card, or if it is just a software process and we have multiprocessor system. And sometimes the cryptography may be implemented as a software or in line, or as a dedicated CPU, hardware, or ASIC as well. Knowing all of this, knowing that the planes are separated, let's maybe take a look at a simple example of DTLS session about the attempt to establish DTLS control connection to the smart controller. What happens here? We have a daemon call it vDaemon. It's fully responsible for all control connections. vDaemon will forward a packet through so-called Linux forwarding transport system towards the data plane, just like if it was a normal transit traffic passing through a device. It will be then arriving from some funny, interesting interface name called internal, right? But in fact, this is just like any other transit traffic will be sent towards the controller ultimately. What happens next if there is an OMP session within it, right? So we establish control connections, not just for sake of control connections, there is something happening within them. And in my part of policies troubleshooting, we are more interested about OMP routing protocol because most of the policies are passing through OMP as a OMP policy packets. Let's say we attempted to establish OMP peering session. What happens next? We have a daemon, call it OMP. OMP daemon will send a clear text TCP packet to vDaemon, which will encrypt it. Depending on the protocol, it will be TLS or DTLS. And sooner or later, we have, after the TCP exchange, after the negotiation, and so on, of OMP, we will have a TCP session established and fully running OMP peering session. Now we want to attempt to send the policy update packet. Policy update packet will arrive to vDaemon. It will be decrypted, sent to OMP for further processing. Sounds complicated, right? But let's go even deeper. What happens next? We got the time OMP update packet. The part which we check with help of show configuration commit changes, it's actually here. It's actually configuration daemon, which stores the information from vSmart in its database, right? Then that daemon will pass the information to forwarding policy manager daemon. And it's also responsible for backward compatibility. You may be running controllers of a newer version. Maybe your controller already support remote preferred color, but device is still running 17.12 and does not support it. It does not mean that the policy is going to fail. We simply will prune part of a config and send it to, for forwarding policy manager daemon for processing. Here, we have forwarding manager, right? We need to program the device to do something with that policy. And it's divided in two major parts, forwarding manager route processor and forwarding manager forwarding processor. For policies, that part is not interesting because it's transparent. The interesting thing happens here. It will try to establish relationships between different parts of a policy, and it will do it asynchronously. It means we are not going to install first sequence, install second sequence, install third sequence one by one. We try to do it asynchronously, and we don't wait for the sequence to be installed. It's an important concept because I'll show you interesting examples what can fail here. Finally, we program it into the forwarding plane, right? And execute here. Policies is a part of policy processing engine microcode, which implementing packet processing features. An array, right? You know, it's from programming. It's just a set of links pointing to different features. Policies is just one of the features which is applied to a packet, including quality of service, including encryption, and so on. So all features of a data plane. Sounds complex, right? Again, use it for your reference, but key points here we need to know. All iOS XE platforms sharing the similar architecture. Route processor is just Linux kernel with multiple additional processes, like a Linux server, which are doing the control plane and some inter-process communication. RP will program a data plane, right? And here on the data plane, we will execute various features, including our policies. The good news is that we can use the same troubleshooting tools no matter which platform we use. Let it be the smaller ISR 1100 router or C8500 series router. We internally share different hardware architecture, but software architecture and troubleshooting will be the same. Okay, back on track. So what are we going to verify on this level? And more importantly, why would we do it? Again, it's not something which you are likely going to see at all. But once in a blue moon, it may happen that you see something in the logs similar to this, right? Data plane, session stuck, we cannot program some object. You are going to do then some investigation, if you want. Usually, at this point, you are going to open attack keys right away, but you still can do some verification yourself, if you want. And I'm going to teach you. This is the fun part which you may not necessarily need to do. But before we start, let's establish some base ground and terms. What is AOM? AOM is an asynchronous object manager, let's say control plane thing, which helps us to continue processing and doing some other tasks while trying to install some objects into different data structures, right? We don't need to wait for inter-process communication to finish before continuing with other tasks. That's why basically it's asynchronous. And that thing, it has two major states. AOM done and AOM pending. But done is a good state, so everything is done. And pending is bad state, we are still waiting for something. If we are waiting for this too long, it means something bad happening. The other term, again, we like to do so. Right? We like to do this. We like to use different terms internally compared to what we call them in our documentation. So here, on that level, we call policy a class group, and policy sequence we call classes, right? So hence, the commands, internal command, not really internal, those commands are available to you. You can use them. We are not hidden. But to understand how and what we are doing, we need to know what is class group, what is class, and this is basically a policy and policy sequence. The whole policy should be reflected starting from OMP daemon to convd, from convd to forwarding manager FP, from forwarding manager FP to the QFP data plane. We will follow the same path like I showed it to you in the previous pictures. F1 RP is just pass-through level, I already told you. So, for the sake of demonstration, we will use very simple policy. I'm trying to send my service-side traffic from that subnet to the DIA, so basically to NAT it and send to internet. There is only one sequence in it, right? And we're trying to install it into the software and hardware on iOS XE device. What are we going to check the first? The first part is FPMD daemon, forwarding policy manager daemon output, which is basically, you know already, shows demand policy from vSmart. This is how it is seen by FPMD. If there is something already wrong or incomplete, there's no point to continue deeper investigation with policy parameter verification, because probably we didn't get something from vSmart. But still, we need to verify if OMP passed that information to convd protocol. To do so, you can enable logging. But the approach here, you don't want to read through all of those logs. They are cryptic, hard to understand. I don't know what is really printed in those logs, only maybe some key points. What I do, I set a logging marker. Then, depending on which version you are using, there are two different approaches to view the logs, right? Oh, sorry, to enable those debugging. To view the logs before we view those logs. I want to clear OMP session, so to reinitiate, again, policy installation workflow, vSmart will send me OMP policy packet. We will parse that policy packet. We will try to install it from forwarding policy manager daemon into convd. And here, since I don't know what exactly to look for, I will simply look for errors. If something is marked with error, then we are in trouble probably, right? You don't really need what exactly you are looking for. You just need to search for errors. More or less, it will be human readable. If no failures observed, then everything is good, and OMP installed information to convd. Now we move on deeper to a rabbit hole. Even deeper. We start with control plane troubleshooting of forwarding manager, but it's relatively easy as well. So we can verify summary binding to particular VRF. We verify that we have policy installed, we verify that there is a status, and even we can use the policy name. We can see the policy name here. And you will also notice that it is binded to particular VRF. But the catch is that the number does not essentially match to your VRF name, which just happens to be the number also. How to verify the VRF ID? Very easy. Show IP VRF detail, and then it will tell you the VRF ID for your configured VRF name 1, right? That's kind of tricky part which you need to verify before claiming that the programming didn't happen. Okay, so once I have identified the identifier for policy, I can verify policy sequences here, or basically classes. And you will notice that in fact we have 2 classes always, even if you configured only 1. We configured only 1, but there is a default class which is default action, drop or accept, right? Class ID 65535 is always the default class, and hence number of classes is limited by this number. At least on an iOS XE device, you cannot configure more than 65K classes. A real-life example of what can fail here, what may fail here. You verify that, and you can see there is only 1 class default. It means we were not able to program with class 1. Why? Maybe because, for example, we were trying to match not based on source prefix, like in my example, but maybe we are using application-based match. And if we cannot program that application, maybe because application definition has not arrived to us from SDAVC, then we will not be able to program it into the control plane of a device, right? Logical. You can verify also details of that policy and compare it with FPMD view, right? More or less, it should be also human readable, and we also key points to pay attention to. Everything should be done. So this is a good state. Also, group ID is seen here. Based on group ID, you can see what is within that match condition, right? Again, if you remember, I am trying to match just based on the source prefix. And to ensure that it is created here in RP, we need to take a look at the state. If there are not too many of those objects, maybe you can see all of them at once, right? In my case, we have only 1 object. That's why the list is small, right? You can use the second alternative command. Okay, but up to this point, we verified everything on the control plane of the router. Likewise, we need to do the same on the data plane, in QFP, right? In QFP. But before we do so, we need to ensure that feature in the feature invocation array applicable for this interface. If it is data policy or application aware routing policy, this is the name of a feature as it's seen on the interface. If it was a localized policy, you will see, if it is localized access list, localized policy, you will see something like SD1_access list. And depending on the direction from the service side, inbound or outbound. And then also the thing is, for access list, we may need to know the interface handle ID. It's also yet another identifier, and you can determine it with help of that command. Remind you, right, for data and application aware routing policies, we will need VRF ID, which is not always matching to VRF name. What happens next? We will verify class group or policy and to find its ID. We will list all policies, right, which is class groups in the QFP, and then the identifier for the SD1 policies will be here. Since I have only 1 policy, it's easy here, more or less. Then we can check separately match conditions for the policy, right? Because those match conditions later program it into ternary content addressable memory. And actions. Here we are checking match conditions, and we can see also the identifier of objects we are matching. I again remind you, we have only 1 match condition is the source prefix. This is the identifier of source prefix. We can even see the content of that object. And here you can find its name, right? And based on the name, you can see that, voila, finally we can see our prefix programmed in hardware. Nice, right? Actions, as I already told you, are checked separately. This is how you check them. And we can see that indeed we are doing not DIA for that prefix. We have also default action. Or we can do it also per class. If you have a bigger policy, it's not convenient to see all at once. You can see them per sequences. sequence 10, sequence 20, and so on. It will be different classes within the class group, which again, I just remind you, a fancy name for policy, right? If it was a localized policy, it can be also checked. Examples. In TCAM, what is TCAM? I remind you, this is ternary content addressable memory, the thing which helps us to do a match for the traffic very efficiently. It's a very fast memory. Sometimes it's even implemented in hardware. In contradiction with content addressable memory, ternary content addressable memory, it has three conditions: match, does not match, and don't care, right? So that's why it is TCAM. The output of TCAM may look, again, very cryptic, but still there is useful information for us. What you can pay attention to: number of entries, right? Since we have two sequences, we must have at least 2 entries in the TCAM as well. You can also check how much memory your match conditions consuming in hardware, and also how many entries are still available for us. And here you can also guess, based on just sequence IDs, that this is the sequence ID. So yeah, certainly you won't be able to read all of these. You won't know what is 02, and I don't remember either, but still we can use it to verify something. What if up to this point you identified some issue? Maybe you identified that you have only one sequence in TCAM, or you identified that policy is not installed at all on the QFP but in RP. What are you going to do? I have no better proposal for you. but I promise you, guys from TAC will be very surprised if you give them all of those outputs, and if you face that issue and troubleshoot it up to that level, you are basically doing most of the part of task what TAC engineer will do. Okay? If you are not bothered yet, if you don't look like my cat on this picture yet, let's continue with part number 2, which most likely you are all here for. Enough about complex, boring stuff. Let's talk about issues which we've seen in the field, and we applied those troubleshooting approaches to troubleshoot it. But before we continue with centralized control policy troubleshooting, quick recap on what is disjoint underlay. Disjoint who knows what? Already, you know it already. You read it on the slide. So disjoint underlay is simply a topology when two devices have no direct connectivity in between them. Like on my topology here, device branch 1 connected via MPLS to the gateway 1, and device on branch 2 via biz internet. So the only way for them to communicate with each other via the hub device, via the third device, right? Usually it will be hub and spoke topology then. So when the very first case, which is a real life example, we've seen it long ago, when I maybe was in TAC long ago, is the redundancy. It's an issue with disjoint underlay when there is a policy was configured to prefer the path from gateway 1. So the idea is that traffic should follow to gateway 1. If gateway 1 is not available, follow to gateway 2. And maybe there is some kind of service-side routing, and we advertise some prefixes from data center. So my objective is to forward through gateway 1. We configured a policy. Someone configured a policy which says if route is from site ID 1, which is gateway 1, then set a preference to 100. Yeah, by the way, gateway 1 has a different site ID. Gateway 2 is site ID 2. Gateway 1 is site ID 1. Right? It's not like the same site ID configured. That policy was applied on inbound direction. Do you see some issues, some mistakes, logical mistakes with a policy already? Perfect. When I'm teaching something new today for you, we will verify OMP routing table, right? For the prefix, let it be default prefix, which is advertised from somewhere here. We can see preference assigned as expected. We can see indeed we prefer 10.0.0.1. Why? Because we have C, the status CIR. Other one is just chosen but not installed. This one is installed. Those two are invalid because we don't have connectivity to biz internet. We cannot resolve data plane via biz internet. So far, so good, everything expected. But when we shut it down, that link to MPLS from gateway 1 to test the redundancy, what happens? This is on BR1. We don't have prefixes installed because we cannot resolve a biz internet. right? Let's think about this problem from a perspective of the smart controller. So we had advertisement for the prefix, for the default prefix via MPLS, via internet, and same from gateway 2. Then there is a policy, set preference 200 for gateway 1. Remember the most important concept of troubleshooting for centralized control policies. There will be a best path selection, right, on vSmart. And as a result of best path selection, we can select only the path which has the preference of 200, and it's internet prefix. We simply don't advertise the prefixes with lower preferences from gateway 2. And only best route is sent to gateway 1. And certainly it cannot resolve the prefix because there is no business internet connectivity. And this is how we are going to solve it. This is only one of the approaches, which is with help of policies. You apply policy on the outbound direction. In the slides, there are other solutions which are not really policies related. We are more routing related. Still, they are available for you for reference. Let's test. We are testing. We applied new policy. We shut it down that link, and we can see now that we have preference set to gateway 1. And when it's disabled, we can see only 3 paths remaining, and we switch to the second one, which we still can resolve, right? Despite that the preference set for the prefix via business internet to gateway 1, since we cannot resolve it, we select something which is still resolvable. Case number 2, similar topology, but now we have fully connected underlay, full mesh, right? Device BR1 connected to MPLS and to the business internet. The idea was to have a multi-level preference. If everything is up and running, we prefer path via business internet or via MPLS towards gateway 1. If it fails, we prefer path via MPLS to gateway 2. If it fails, then we prefer path via business internet to gateway 1, and the least preferred path is via business internet to gateway 2. So the policy was configured. And who was on my lab yesterday on policies troubleshooting? So yeah, don't tell. The idea is here, but there is a mistake. For those of you who hasn't been to my lab, can you see that mistake already? I'm actually really glad to see it, because when I'm again teaching you something interesting which you haven't seen before, right? I'll try to explain. So this is like routing policy behavior under normal conditions. So everything up and running, right? We have preference set, it goes via gateway 1, via MPLS, just as needed. And we are testing it with show is the one policy service path, right? One of the troubleshooting steps. Certainly I'm making shortcuts. We are not verifying everything like one by one according to troubleshooting workflow. But we arrive at step number 3, and we want to ensure that we are selecting the correct path. And yes, it looks good. We programmed everything apparently correctly. We point to MPLS, to gateway 1. And even in routing, we installed everything correctly. Gateway 1 is preferred. But now we are testing the failover. And there is a router on the service side, autonomous mode router. We shut down the link towards that router, committed the configuration. Then we start to verify the routing. Okay, routing is not in place. It's not in place anymore. So gateway 1 cannot reach to that destination, right? Then we check what happens on the smart controller. Did we withdraw that route? Yes, we did. This is so far expected. We have only 2 paths remaining. They are both from gateway 2 only, right? So far, so good. But on branch 1 is the device on the left, which is trying to send the traffic to a data center. We verify show policy service path. It's still pointing to gateway 1. Kind of strange, right? Still pointing to gateway 1. Maybe it's mistaken. Policy was not programmed. Let's try to figure it out. If we check OMP table, OMP routing table on BR1, there is actually already a hint. You just, sometimes you don't need to understand how things work. You just need to compare the state in a normal condition with state in a bad condition. And this is what you will see instantly. The order of paths has changed, right? word of paths has changed, and now the path which is preferred is number 3 in the list, not the number 1. It's already may ring a bell. And certainly, if we ping that destination, it leads to black holing, right? We cannot reach it because traffic goes to gateway 1, which has no connectivity to that subnet. Why? This is because vSmart still executes the policy as you instructed it. If you think about this policy, it's basically a next hop rewrite. Classical case with BGP route reflectors. We are doing the next hop rewrite unconditionally, and we are not verifying next reachability for that next hop. Let's take a look at the original policy one more time, right? Think of all of this construct as set IP next hop. Basically, it's the same. So we set a next hop, but which contains of 4 different options. And within those options, there is a preference which says gateway 1, MPLS is the top preferred, no matter if you have advertisement from gateway 1, right? So visually, if you think again about that advertisement from the perspective of the smart controller, we have prefixes arriving on the smart. When we disappeared, we were withdrawn. Only 2 prefixes remain, but since on the outbound policy, after the best path selection, we have set TLOC list action. We are rewriting that next hop, and black holing is happening. How can we fix it? There are multiple solutions possible. One of them is simply to establish more granular control and set TLOC preference conditionally only if we receive the advertisement on the smart from this particular device pointing to that particular TLOC. So, like this. Like this, we have different TLOCs, TLOC for gateway 1, and then the same TLOC list, but with preference. And we will set TLOC list only if route already pointing to TLOC of gateway 1, but with preference. Then we are basically solving that problem of reachability verification. Let's check it. Let's test the solution. We apply a new policy. We are doing our testing. We shut it down the link. We have only 2 paths remaining, and we are pointing to MPLS of gateway 2 as we wanted. Right? And the rest of the commands confirm that we have reachability and we are pointing to the right direction as we wanted. Case number 3. Case number 3, it's about set TLOC action. And the idea here was to redirect the traffic through data center. Despite that we have direct connection between BR1 and BR2, for whatever reason, we decided that it's more optimal to send the traffic through DC1. And there is a policy action available for us, call it TLOC action primary, right? We set a TLOC saying that TLOC of gateway 1 is primary via color biz internet. What happens next? We start to verify if policy works as intended, as we wanted it. And trace route shows that there is only one hop. It means traffic goes directly to BR2. And the same show SD1 policy service path confirms, right? We go directly to system IP of BR2. Strange. Let's check OMP routes. Let's check OMP routes on BR1. We will see, yeah, you can see probably that I'm using a bit complicated, bit long command, but it's nothing but I'm trying to exclude unimportant attributes and include only important one to show a shorter output. Then you will see something new, which is unusual. So call it ultimate TLOC, right? And ultimate TLOC is a target TLOC that an intermediate hop, such as gateway 1, will use to establish data plane to reach to a final destination. Why doesn't it work? And unfortunately, this is an example of a solution which you must be familiar with, right? This is something you must know beforehand. And the issue is basically caused by misconfiguration. There is one important thing missing, which does not respect the rule. And the rule says that if there is action set TLOC, you must configure special service called traffic engineering. It's not the same service which is used for service chaining. It's a service which is configured under the global routing table And here is how you can configure it from the CLI. Here is how you can configure it vManage UI. And to add complexity, since it is not a normal service for service chaining, when you check show SD1 OMP services, you won't see that service advertisement. But it's a rule. You just need to remember it. By the way, this is also a prerequisite for on-demand tunnels. The on-demand tunnels, which are establishing connections between edge routers on demand, won't work if you don't have service T enabled. Just a hint. Although it is not about policies, certainly. Yes. So we set that service. Traffic engineering. Now we are testing the solution. We can see exactly the same. Nothing changed with policies, but the only difference that now finally we can resolve that path. It's resolved and install it into the OMP table, right? And traceroute follows the path via gateway 1 as we expected. There is a sub variant, slight variation of that case. I call it 3B. What if colors are different? What if we have this joint underlay here and still we want to follow DC as an intermediate hop? You will see that despite here we have also ultimate log. Yes, traffic engineering certainly configured already. Service traffic engineering still configured. But the path is unresolved. Why? Unfortunately, there is also a limitation in place, which says that we can't use basic RT-log action if we are trying to glue, if we are trying to stick two different colors altogether, right? And this is for reference, for the rule which we have in our documentation here. At the same time, if you're still interested for this feature to be implemented, this is an enhancement request which you may discuss with your account team if it is really needed for you. I'm just saying. Okay, enough about centralized control policies, right? We had enough cases. Let's quickly check some data and application-aware routing policies. And this case I like particularly because it's not from that distant past, maybe 2 years ago. The case was escalated to me, and it was said that something strange happening. I have very large enterprise here. I have the data center with most powerful SD1 devices. And the thing is that we performed software upgrade. The hub router was reloaded, since the upgrade requires software reload, or since the upgrade requires device reload, right? And after the upgrade, device cannot install any policies. What would you think right away, right? It's something bad with new software. So certainly, we asked them, did you try to downgrade it back? They said, yes, we did. We downgraded it back, still policy is not installed. And there are no more changes, only software upgrade was performed, right? We started to follow a troubleshooting workflow. You remember, right, the very first thing is to verify the peering. If policy can be applied, are we having OMP peering established between that 8500 series device? Yes, we do. And uptime is 18 minutes, quite stable. So far, so good. And from perspective of vSmart, we have policy assigned. This is some kind of application-aware routing policy, data policy. And we even check it on vSmart if crafting is OK. So we are doing translation to XML. So far, so good. We did even debugging. We ensured that traffic was sent as a part of OMP update packet, right? On device, there are no policy changes. We are sending packets, but we are not installing still the policy. Then we started to verify control connections, because control connections have a transport for OMP sessions. So we went one step lower. We need to ensure that transport is functioning, but control connections are there. Except that the uptime for them is different. This was already a bad sign. But OMP peering is still stable from a device side perspective, right? From 8500 series device. We can see that OMP is still stable. So we are supposed to install the policy. Still the mystery remains. No policies. No policies. And none of the commands showing those policies. From the logs, at the same time, we can see that connection with other vSmarts is not that stable, right? What if something strange happening on the device? What will be the tool? You remember, we follow that approach, we go deeper and deeper and deeper, and there is a heavy artillery, heavy machinery, packet trace, and WPI. But first, we want to ensure that maybe packets are dropped. We will check the drop counters, and indeed, instantly, we see that there are a lot of drop counters happening. There are a lot of drops happening because of some strange drop counter, which I even was not aware of. Then we started the packet trace to see what exactly is being dropped. I specified the drop condition called 206 of that reason, and we looked at the details of a packet and found that most of them are coming from control plane components. This is the packet which is being dropped from vSmart 2. Interesting. So let's summarize so far. No problems observed from the perspective of vSmart. vSmart is doing what it is supposed to do. It's functioning as expected. The hub router does not have any policies installed, but it should, as per vSmart point of view. The hub router dropping packets extensively with that drop code, right? And we can guess by the name of drop reason that it's some kind of policy configured. And the reload was the trigger. If you search simply on the Google, you don't need to know all of the complex stuff. You just need to find that drop counter. You will instantly be pointed to Cisco support community forums, which will explain the reason for this. It's a special policy which protects the CPU, control plane of CPU, from distributed denial of service attacks, for example. Basically, control plane policing, which is applied by default. And you will find on the same support community post that there is a command to verify that particular policies in detail. This is the watermark configured, and you can see we are indeed dropping packets. It must be reconfigured. Why is it happening? Remember, we reloaded the router, data plane went down, then it came up, and then 4,000 devices are trying to establish connections all at once. For router, certainly it looks like somebody is trying to kill it. Policy was reconfigured, and we can see policies installed already from the logs. And certainly, show MP summary will tell us that policy is installed. And data plane went up finally. Okay. Probably final case for today. About application aware routing policy or data policy, essentially it will be the same. Typical symptoms will be that user's traffic affected. No connections to some internal enterprise servers. And only limited set of application affected, while you can still reach to the server, you can ping it, and ports are opened on the server. And it usually happens once you enable direct internet access or cloud on ramp. This is how it looks from the perspective of a user. We can't use web-based application. Right? And the data policy which is usually implemented, in essence, is very simple. Not DIA, much based on application. Okay, let's try to investigate. Again, using the very well-known approaches already. Show is demand policy service path, and it instantly tells us that for this particular traffic, towards HTTPS port, we are doing the black hole. One common, more or less expected reason would be if there is no route to that destination. But we have routing in place toward the data center. So hence there must be something else resulting in the black holing for that application. If we check some other applications, like simple ping, yes, we can select next hop properly. Likely it has something to do with application recognition. If traffic is black holed, there is a reasonable assumption that it must be dropped on the device, right? Let's check QFP drop counters. No, empty, nothing interesting. Device is not dropping it. And we can see that packets are being forwarded as well. You don't know precise packet trace filter usually, so to trace particular packets in the flow. What would you do? In this case, NWPI is your friend. Because if you enable NWPI, which will trace multiple flows at once and give you a complete overview, you may notice that some flows, they have only upstream destination, but no downstream destinations, right? And if you check the details of inside view, we are doing the redirect to NAT. We are doing the DIA for internal applications. For internal source IP addresses, we are doing DIA. To the internal IP addresses, we are doing DIA, right? Why it happens? Great question, but it depends. Sometimes it's just hard to recognize the application and differentiate it with cloud-based application like Microsoft Office 365, for example. Or it may be a bug or outdated in-bar DPI package. Maybe in your DPI package we cannot recognize that application. The good news that there is usually a relatively simple workaround applicable in most cases. It says that you need to ensure that RFC 1918 prefixes excluded from DPI evaluation, right? And the inherited benefit, reduced load on the device because you don't need to perform that DPI classification. How? Very simple. Just insert the sequence above all of the rest, saying if destination is your RFC 1918, just accept the packet and that's it. But it's also possible that the same problem happens with Cloud on RAM SaaS. Solution is similar. This one we are going to skip, and in essence, let's proceed to the summary. This case is very simple. You can follow it later through my slide deck. It's also kind of misconfiguration with cflow template. Let's summarize rather and talk about typical policy issues which are seen. This one is like classics. Someone forgot to configure reject, or someone left default accept action. This is classic, just misconfiguration. The other one is the policy application. We've seen examples already when it causes a lot of harm, when the direction of policy application is not considered properly. Policy application scope is too narrow or too wide. This is third top most common reason. What it means, for example, you have a policy applied to particular site list, but you want to be more granular, and when within the sequence you have yet another, or you are supposed to have yet another site list, which is shorter, right? And you forgot to apply it. This is what we call policy application scope is too narrow or too wide. Simple misconfigurations, this is probably the fourth top major reason. And always keep in mind, hence, policy procession logic. If sequence, let's say, 20 is already performed detection, and you have sequence 30 below it, despite that it may have the same match conditions, traffic won't be matched to sequence number 30. The traffic was already processed by 20. Control policy specific faults. Again, direction before the best path selection or after, and conditional TLOC rewrites. TLOC action while service T is not configured. We've seen example of it. Attempting to glue different colors together. We've seen case 3B about this as well. About application-aware routing and data policies, common issues. Return traffic is asymmetric. You have approach with show application forwarding cflow flows to verify if traffic is symmetrical or not. Equal cost multipath is not there, hence application-aware routing policy can select different paths. This is also typical common mistake. And misunderstanding from application-aware routing policy. Sometimes you think that the policy does not react quick enough. This is because of it configured timers as well. It may take up to 1 hour. You may think that BFD poll interval may change situation, but it affects only frequency, but not the reaction time. And common issues when we are using application-aware routing policy with data policy, I gave you a workflow which can help to determine what exactly will happen with particular traffic after both policies applied. Misclassification may be happening because we haven't seen DNS request packet fallback issues, which we are not covering, but still stickness and flow fallback, and flow stickness related issues. Those are also common mistakes seen with application and data policies. Last but not least, this is yet much less well known. Fragmented packets, like UDP fragmented packets, are matching to a sequence with port match condition, despite that there is no port information available in IP fragment. Why? Again, it's not any kind of software issue. It's just because of an attempt to do a fast forwarding. We match to a cached flow already and forward traffic according to the match which contained destination port match or source port match conditions for the traffic pass which were passing before. And last but not least, references and recommended resources. We keep publishing troubleshooting tech notes, like lessons learned, from TAC or from escalation team in some call it half official documentation, which we publish under the tech notes. My other session, I already mentioned it on troubleshooting, on routing troubleshooting, and a few other older sessions from my colleagues. This one will be particularly interesting if you want to know more about iOS XE software architecture, this one about policies in general, and this one about older session from technical marketing on troubleshooting, long session during the COVID years. I really like it, that's why I recommend it. Again, remind you, we have a WebEx application. Let's keep in touch. Post your questions there, because we are, as I expected, frankly. We run out of time. I can answer to your questions after the session, or in the WebEx application if you have to go to the airport or whatever. Let's stay in touch. It will be kept open for the rest of the month, till the end of the month. This line you've seen a lot. If you still want a T-shirt and you haven't got one, try to get one. And the only recommendation regarding continuing education, since this is the very last session, it will be posted in the on-demand library, or if you have any questions, contact me on that email address. And I wish you safe travel back home. Thank you. That's it for today. Don't forget to leave a feedback, please. If you want to see similar sessions from engineering, from TAC, please, you know that the 5-star mark is what we want, right? All the rest, and unfortunately, don't consider it as a positive feedback. Thank you. Thank you.